Okay, so we're very happy to have Mateusz Łewyk back to speak on part 2 of his talk on pathologies in satisfaction classes. So go ahead, Mateusz.
Yeah, thank you very much for having me once again. So this is part 2 of this talk. So last time I essentially introduced these new notions that are crucial for this product, for spelling out the results, and got some intuitions, and also get information about some intuition, and also wanted to convey some intuitions. So let me now quickly recap what it is all about. So we are going to investigate sets definable subset of models of PA, definable with the help of a satisfaction class. So what is a satisfaction class? Satisfaction class is anything that makes any subset of the model of PA which makes the following sentences true. So first of all, it consists if so the meaning of S of xy is that x is satisfied by an assignment y, and this is the necessary condition spelled out by the first condition. So the second one tells me that my satisfaction class correctly guesses the satisfiability of atomic formulae. This S to the alpha equals to T alpha means that the term S under the assignment alpha gets the same value as the term T under the assignment alpha. The next says that phi is not satisfied. So not phi satisfied by assignment alpha if and only if phi is not satisfied by an assignment alpha. So disjunction is satisfied by an assignment alpha if and only if one of the disjunct is. And the existential sentence, an existential formula is satisfied by an assignment alpha if and only if we can extend this alpha and finding a value for a variable v in such a way that phi will be satisfied by beta. So these are the straightforward formal counterparts of the usual Tarskian inductive conditions for satisfaction relation. So we shall work exclusively over PA, and we shall abbreviate with T of phi the sentence phi is satisfied by the empty assignment. Right. So now a satisfaction class, once again, so S is a satisfaction class if MS is a model of CS mind. This is my basic definition, and all models under consideration are models of Peano arithmetic. Right. So as I've said last time, also this is about this project is about like having general results about the possibility of constructing pathological satisfaction classes. So in particular, we'll be interested in constructing satisfaction classes in which some pretty obvious propositional validities fail. And in order to spell out what is a pretty obvious propositional validity, let me recall notion of a propositional template. So we say that phi of PQ. By this we mean a propositional formula built with atoms P and Q, connectives, conjunction, disjunction, negation, and quantifiers treated as unary operators. So in particular, they syntactically behave just like negation, so they bind no variables they have just trivial occurrences. And we want phi of PQ to have the following properties. First of all, phi of PQ is not tautologically equivalent to P. So its true value really depends on the value of Q. Secondly, if both P and Q are true, then so is phi of PQ. And if both P and Q are false, then so is phi of PQ. So let me stress once again that this phi of PQ is truly finite propositional function. Okay, I assume also that it is of non-zero complexity. So in particular, this is not equal to Q simply. And here comes our propositional operation. So let me, working in a model M of PA, let me define a function from M times the set of sentences to the set of sentences in the sense of the model as follows. F of 0 of phi, this is just equal to phi. And f of x plus 1 of phi, this is equal to phi of f of x phi. Let me give you just an illustration of how it looks like. So for example, phi of PQ can be equal to P or Q. And this is a canonical example. And then f of 2 of 0 equals 1. This is 0 equals 1 or f of 1 of 0 equals 1, which is the same as 0 equals 1 or 0 equals 1 or f of 0 equals 1, which is the same as 0 equals 1 or 0 equals 1 or 0 equals 1. So essentially, f of x 0 equals 1, it looks like a disjunction parenthesized to the right of depth x, where this longest path in this tree has length x. We call phi the template of f. So right, so this is like the crucial basic observation for this project. So by the conditions put on this template phi, for every n and for every phi, actually f of n phi is equivalent to phi, right? And this is like a very basic inductive argument shows this.
This was for standard, right?
For standard, yes. I mean, so yes. So for all the numbers that it makes sense without satisfaction class.
Right.
Which means for standard numbers, right? And the second one remark is that although phi of PQ can be really syntactically complicated, so if you just look at the possible truth tables for phi of PQ, then it is equivalent to either of P or PQ or P and P, P or Q or P and Q or Q. Just. So later on, we'll also define to the operators with template phi, which is equivalent to P or Q or Q as monotone, as Q monotone, and to the ones which with templates equivalent to P and Q as not Q monotone. Okay. Right. So now one of the crucial definition. If P appears syntactically in phi of PQ, we refer to F with template phi as accessible. So in particular, this guy, this F defined from phi in this way, it is an accessible operator. And this is because even though you can iterate adding this template phi many times, you'll be in accessible operator, you'll be always able to see this formula close to the root of the syntactic tree of f of x of 0 equals 1. Right? And this is unlike in the case where f is additive. So let me give you one more example for something which is not accessible, which is additive. So let me define now phi of PQ as simply Q or Q. Right? So then how does it look like? So actually, in this case, say phi of 2, 0 equals 1. This is phi of 1, 0 equals 1, or sorry, f of 1, 0 equals 1, or f of 1, 0 equals 1, which is the same as f of 0, 0 equals 1, or f of 0, 0 equals 1, or the same in the right disjunct, f of 0, 0 equals 1, or f of 0 equals 1, which is the same as 0 equals 1, or 0 equals 1, or 0 equals 1, or 0 equals 1. So this time, if you take a large number x and you start iterating this procedure, then this formula looks like this. And in particular, you will be able to access this sentence 0 equals 1 only at level x. And this is a crucial difference between accessible and additive case. Okay, so the following operator with the following templates are accessible. So at this point, let me just draw your attention to the last one, not Q and P or not P. So this is accessible because P appears in this formula, even though actually this phi of PQ does not depend on the value of P. Right, and the following template generate additive operators, Q or Q, not Q and Q, and so on. So where does this name come from? So I guess that the intuition why accessible should be now clear. Why additive? Well, this is because additive operators satisfy the following equation. So for every x, y, possibly, I mean, just this is provable in PA. F of x plus y phi, this is the same as f of x of f of y phi. Right? So a deep binary disjunction of depth a plus b is the disjunction of depth a of disjunctions, binary disjunction of depth b. Right? And I guess it's not worth to spend much more time. This should be clear that this is the case. Okay, So now the crucial definition for the main result. So suppose we have a model of CS minus, so a model with a satisfaction class. And we say that I is the F correct cut in this model, if and only if I is the longest initial segment of this model M, which consists of those numbers X, such that our satisfaction class validates this idempotency of F whenever F is iterated X times on every sentence, right? So what you observed previously in the standard world, you know that always it's the case that for standard number n, F of n phi is equivalent to phi, right? For arbitrary phi. So now we ask which cuts. So now we say that the F correct cut in this model is the cut so that is the longest initial segment on which this propositional equivalence is validated by our satisfaction class on every sentence, right? So in particular, for the particular case of where phi is, for example, P or Q, as described in the right, then we essentially, then if I is the F correct cut in a model of in a model of CS minus, then it means that if you start iterating this procedure of taking longer and longer disjunctions, parenthesized in this way, then as long as as the length of this iteration belongs to this cut I, our satisfaction class behaves correctly. However, on numbers which are arbitrarily close above this cut, it might misbehave. Okay, so shall I say something more about it?
I think I'll just add in more, so you have this cut above, anywhere above that cut, you can find some sentence for which there is a counter example below that number, right? So if you have any C that is above I, there is some sentence where the iteration of length, some X below that C is going to, it is going to be, it's going to be wrong. There may be some sentences where where the correct set for that sentence is everything, but this is saying the other way around, that for each element, for each number, there is some sentence that is where it messes up.
Yes, thanks a lot. So this is okay. So I think that it would be actually good to write a picture of this situation. Yeah. So when I is the F correct cut of this model MS of CS minus, it means that whenever you take a number which is in this cut, and you consider the sentence F of X phi, where phi is really arbitrary, then you know that this propositional validity will be in the satisfaction class. So we'll have S of this, that this is satisfied by the empty assignment, right? However, when you take something above this cut, call it y, then you always know that you will be able to find some y prime and some formula phi prime such that we have S of not f of y prime phi prime equivalent to phi prime empty assignment. Okay, so this is what I mean that if I is the F correct cut, then it is characterized as the longest initial segment, so that the satisfaction class behaves correctly with respect to this propositional construction. Okay, shall I go on?
Sure, I think so.
Okay. Right. So one thing. So if F is additive, so in particular, it satisfies this equation that f of x plus y phi, this is literally the same sentence as f of x, f of y phi, right? Then the F correct cut is always closed under addition. Right? Because if you take x, which is in this cut, this guy, and you would like to check whether 2x is in this cut, then after fixing an arbitrary formula, you see that f2x of phi, this is equivalent. Sorry. So first of all, okay, f of 2x phi, this is literally the same sentence as f of x of phi. So in particular, since I is the F correct cut, and our satisfaction class, so our satisfaction class behaves correctly, and x is in I, then it follows that we have S of f of x phi equivalent to f of x phi. Right? And moreover, we have S of f of x phi equivalent to phi. And then the rest is just compositional axioms, CS minus. So as we will, one of the corollaries to the main result is that for the accessible case, this need not be the case. So when f is accessible, then the F correct cut need not be closed, even under addition. Right, and then now two structural properties of a cut. So we say that the cut is F closed if either F is additive and then I is closed under addition, or I is accessible and I is just an arbitrary cut. So if F is accessible, then every cut is F closed. So similarly, we say that cut I has no least F gap if either F is accessible and then for every A there is B, so that distance between A and for every A above the cut there is a B above the cut, so that the distance between A and B is non-standard, or F is additive and then for every A there is above I, there is B also above I, so that the ratio A divided by B is also non-standard. So to make long story short, F is accessible if no sequence of the form A minus n is co-initial. Sorry, sorry, this is not what I wanted to say. So I is F.
I has no least.
Let me start once again. Yeah. So I has no least F gap, assuming F is accessible. If no sequence A minus n is co-initial with I, so whenever we have I, whenever we take something that is above I, and we start counting A minus 1, A minus 2, then this sequence does not converge to I. And this is similarly for the additive case. So I has no least F gap for F additive if no sequence of the form A divided by n is co-initial with I. So whenever we have I, we take A here and we start dividing by 2, then this won't converge to I. It will we'll be fine. We'll be able to find something between I and this sequence.
All right. So I think if I can interject here, it's worth just again highlighting the relationship between essentially the syntactic structure of F, right? If F is it has some certain syntactic structure, and in one case, then essentially what matters about this cut I is the successor relation, and so I must be closed under the successor relation, and then we can also talk about above I. Is there a least gap, or is there some element A so that if you close under successors and predecessors, that you then get to co-initial with I, and then conversely for these additive templates, we have the plus sort of the plus gap we talk about. It must be closed under this additive operation, but also above the cut we would check to see if there is some least some element A, so that if you kind of look at the things that can be the least the convex set around A that can be obtained by iterating addition over and over again, and so division by 2 over and over again, you don't get co-initial with I.
Right. Okay, so I need one more notion, structural notion to recall one more notion, structural notion for cuts in the model of PA. So this is separability. So whenever we have a set A, which is a subset of a set D, they are all subsets of the model of PA. We say that A is separable from D if whenever we have a coded sequence such that all elements from its standard part belongs to D, then from the standard part of the sequence, we can code the set of those positions which belong to A via some number C in the model. M. Right, and we say that A is separable simply if it is separable from the universe. So whenever we have any sequence, then from the omega part of the sequence, we can code the set of those positions that belong, that elements on these positions from the sequence A belongs to set capital A. And this is for cuts, this is equivalent to the following conditions. So for cut I is separable if for every A, it is not the case that the standard part of A, when intersected with I, codes a cofinal sequence with A, and the standard part of the sequence coded by A, restricted to the position outside of I, codes something which is co-initial with I, right? So in a sense, no omega sequence in the model codes both a cofinal and co-initial sequence with this cut. And one remark that since we are here talking just on like the standard parts of these code sequences, then it is very easy to see that if we have a subset, an arbitrary model, the subset of a model M, such that the pair M comma A is recursively saturated, then the set A is actually separable. Right? So you just write a type, use the fact that finite sets are coded, and that's the whole argument. Okay, so from this introduction, you should recall, in order to understand the main result that comes in the next slide, these two basic properties of cuts: separability, which is mentioned here, and having no least F-gap. Right? The latter says that essentially you cannot approximate it, this sequence, this cut from above via sequences of particular type. Okay, so now the first main result. What it says: if we have an arbitrary countable and recursively saturated model of PA and the cut in this model, and a template of syntactic depth 1. What is syntactic depth 1? Syntactic depth 1 is either P or Q, or P and Q, or Q and Q, or Q or Q, or also Q or P and Q and P. So I guess that these are the only possibilities satisfying our assumption. So this is like one theorem for these 6 cases. And let F be this operator which is generated by this template phi. So we suppose that I is F closed. So either in the case where F is accessible, this adds nothing. In the case where F is additive, so essentially in this case and this case, we require that I is closed under addition. And then we show that if I is separable, or it has no least F gap, then in this model, we can find a satisfaction class such that this cut I is exactly the F correct cut of MS. Right? So the essence of this of this theorem is that we have these two conditions, separability and having no least F gap, which enable us to construct a satisfaction class for which this cut I is exactly the F correct cut of MS. Okay. So I will now quickly go through these the main theorems, and then explain, sketch, and then sketch the proofs. Okay, so the next main result complements this theorem because it says that actually, if I is the F correct cut in a model of CS minus, then actually it satisfies one of these two conditions, separability, or it has no least F gap above it. Right? So actually, this is not only that these two conditions are sufficient for constructing or characterizing this cut as the F correct cut of some bias and satisfaction class, they are also actually necessary. And then actually you can, one more question you can ask, which is very meaningful. So can we actually simplify this alternative, either separability or having no least F gap above? Or, and whether it is, for example, it is always possible to find it, whether one might ask whether it is, for example, not the case that every cut is either separable or has no least F gap above. And actually, this turns out to depend on whether the model is arithmetically saturated or not. So the main result, which is the corollary of these results and some models of PA wisdom discovered much earlier. So for an arbitrary countable recursively saturated model of PA, the following conditions are equivalent. So firstly, this M is arithmetically saturated, and secondly, sorry, this is my fault. The second condition should be every cut is either separable or has no least F gap above it. Hence, this is equivalent to saying that if F is of syntactic depth 1, then every F closed cut, so every cut with some appropriate closure properties, can be the F correct cut, right? So I would like to finish the exposition of the results here and proceed to sketches of proofs to show how these properties, separability and no least F gap, enters the picture. But maybe you have some questions before it. Or maybe Arthur would like to add something to this.
I'm good. Hein, do you have any questions or?
Look, to tell you the truth, I have to think about it. I mean, new to the area in a way. I know the very basic results, and this looks very interesting. But I wouldn't pose a question in this case.
Okay.
Okay. Okay. So let me now sketch the proofs. So let me first talk about the proof of this theorem, which is, I think.
Sorry. So let's go back for a second.
Right.
To result 3, I think. Right. So I think this is perhaps the goal, right? That we want to sort of say that somehow, well, all three of these are somewhat interesting, but 1 and 2 kind of work together to sort of complement each other. And then the maybe, you know, if you're thinking in terms of, is there one result to kind of try to walk away from if you're having trouble following all the technicalities, maybe just think about this. If a model is countable, recursively saturated, then either every single cut that is closed under, let's just say successor, every single cut that's closed under successor can be the idempotent disjunctively correct cut. So if that happens, then the model must be arithmetically saturated. Or alternatively, if the model is not arithmetically saturated, there is some cut which again is closed under successor, but it cannot necessarily cannot be this sort of IDC, the idempotent disjunctive correct cut. So that's the upshot of this, and then the same goes for whether you look at binary disjunctions or additive versus accessible cases. Right? The same goes for all of these different kinds of pathologies. Either every single cut that satisfies this one basic property of closure can be the correct cut, in which case the model must be arithmetically saturated. Or if it fails to be arithmetically saturated, then there is necessarily some cuts which we'll see are neither separable nor have and have a least F gap or something like that. And in which case, it's not, if it's not arithmetically saturated, you'll find some counterexample, some cut which you can't make F correct under any satisfaction class. And so somehow this property of these properties of cuts and of these correctness properties happens to depend on arithmetic saturation, which was somewhat surprising.
Yep. Okay. Thanks a lot, Heather. Yeah. So this is the so let me maybe add one more thing, so that this connection with arithmetical saturation, it came really as a surprise to us. So I didn't expect this arithmetical saturation to show up in this kind of research. So this mathematical reality really surprised me at this point. Okay, so let me do one more. Let me do at least one case of this. So let's assume that I is separable first. And moreover, phi of PQ is Q monotone. For simplicity, we can assume that this is, for example, P or Q. Right. So what is our basic strategy? So we'll like follow the strategy invented by James Schmerl of building like larger and larger approximation to our desired satisfaction classes. So we shall fix an enumeration of all formulas. The model is countable, so we can enumerate then omega sequence all formulae in the sense of this in this model. And at each stage of our construction, we shall look at their finitary surroundings, which are generated by this formula. So let me write that AI, this will be a set of the form G of phi 0, phi, where this G means that AI is generated from the formula phi0 of phi. This in particular means that every element in AI is definable from these finitely many parameters, phi0 up to phi. And I will leave it at this very basic level. So then we shall construct a sequence of satisfaction classes S0, S1, S2 with the following properties. So first of all, MSI is recursively saturated. Secondly, when you take Si plus 1, Si plus 1, and you restrict it to AI, then it agrees with the previous satisfaction on AI. Thirdly, which is most important in this context, Si is F correct on I for all sentences from AI, which means that whenever f of x phi and phi, they both belong to AI, and x belongs to I, then Si will behave correctly on f of x phi and phi. Okay, and the last condition is that Si is F trivial above I for sentences in AI, which means that whenever f of x phi belongs to AI and x is greater than I, then Si will make f of x phi true. So think of this F triviality. So if you think of if our template is simply P or Q, then this means that the ith satisfaction class will make all disjunctions of 0 equals 1s of length x, when x is above I, so that the disjunction belongs to AI, will make them true. Okay, maybe let me say it once again. So whenever you take a disjunction which is sufficiently long, the disjunction of 0 equals 1s, which is sufficiently long, which belongs to AI, then it will be made true by Si. Right? Okay, so now how do we actually construct this sequence? So the main idea, let me just describe to you the induction step. So suppose you constructed Si which satisfy these conditions, and you have your set AI plus 1, which means that you need to consider all the formulae generated from one new formula, right? So, for example, this formula may be here, 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 or here in the model. Okay, so the first goal is that you actually first in omega many steps using the Anayat-Visser technique. Okay, and this is like a large black box. So there are a lot of the technicalities in here. you construct an elementary extension of your model M. Let me call it M0. Here you have your cut I, here's your M. This M0 need not be an extension, it's just an elementary extension. And this model, maybe M0, so sorry, let me call it M infinity. This model M infinity will carry a satisfaction class S infinity such that S infinity agrees with Si, so with your previous satisfaction class on AI. Moreover, it behaves as desired with respect to elements of AI plus 1, which are of the form f of x phi, which means that for every phi in AI plus 1, for every x in I, if f of x phi belongs to AI plus 1, sorry, then S infinity satisfies phi is equivalent to f of x phi by the empty and by the empty assignment. And whenever you take a large number x and f of x phi, which belongs to AI plus 1, so AI plus 1 is the desired set for which you want to construct the new satisfaction class, then this formula will be simply made true by S infinity. Right? And then what we would like to do ideally is that now we would like to pull this S infinity back to our model M, right? So the way to do it, one idea how to do it, is to use resplendence. However, this is not so straightforward because these two conditions, okay, so how we would like to use resplendence? We would like to use resplendence by showing that the sentence saying there exists a satisfaction class which agrees with Si on AI and which behaves correctly with respect to sentences in AI plus 1 and this cut I, this is consistent, right, with the model. So, I mean, this M infinity, S infinity, this model witnesses that this theory is consistent. However, we cannot really use resplendence because this theory at this moment mentions this cut I, and it might, so the use of resplendent argument might be blocked in this way. However, here we used our assumption that I is separable. So since AI plus 1 is finitely generated, there is C such that for every phi, for every x, f of x phi is in AI plus 1 if and only if for some m in omega, x is equal to Cn. Okay, so the set A, the elements, the length of these junctions which belong to AI plus 1 can be coded via an omega sequence. So since I is separable, you can separate these positions in C which belongs to I from the ones that do not. So there is D such that for every n, Cn belongs to I if n belongs to D. Right? And then instead of writing x is greater than I, we can write simply the respective Cn does not belong to D. Sorry, instead of writing for every x greater than I, we can simply take those, we can simply write this as an infinite collection of axiom saying that if n does not belong to D, then S infinity of f of Cn phi empty set holds, right? So this condition now can be rewritten in the form if n does not belong to D, then S infinity of f of Cn phi empty set. Right? So this is how we avoid mentioning I in the respondent argument with the help of a single parameter. So we can really pull back S infinity to our model M. And then this satisfaction class will be our Si plus 1. Okay, so this is all that I wanted to say about this case. Do I have like also 5 more minutes to show how this the no least F gap?
Sure, I think you can take 5 minutes.
Okay. Right. So let me first find my notes. Okay. So now what do we do when F is? This is no least F gap case. So what we have is what we fix are, once again, this is the sequence. And so we will construct these.
Sorry, Mateusz,
Sorry,
can
you're
you
not
clear? Can you
Yes,
clear
okay.
that
Yes.
page? There you go. Yeah. Sorry, because it was appearing on top of your previous notes.
Mm-hmm. So once again we fix this sequence. We'll construct once again. We'll construct these finitely generated sets, and we'll also, in the meantime, construct not only the sequence of satisfaction classes, but also a sequence of numbers which converge to I. The picture is that here, somewhere here with the D0, D1, D2, D3, and so on. So what I want from these satisfaction classes. So first of all, on that MSI, it's a model of CS-. So these are really satisfaction classes. Also, MSI is recursively saturated as previously. Secondly, that they prolong at each next one, prolong the previous one on the respective finitely generated set. And then we won't say that, instead of saying that Si is F correct on I with respect to sentences from AI plus in AI, we'll slightly overshoot our cut, and we'll say that SI is F correct on the interval 0 di plus 1 for sentences in AI. So in particular, S0 will be F correct up to D1. Okay. And finally, for some theta, we'll show that actually this SI behaves not correctly on respect to disjunctions of length di on this particular theta. SI satisfies F of di theta is not equivalent to theta, and this theta will once again depend on I. So in particular, for this D0, we shall find theta 0 such that S0 behaves incorrectly on theta 0 with respect to disjunctions of length D0, and there's no least F gap assumption is needed to assume that we can find enough space between D0 and D1 and between each consecutive numbers. Okay, so this is all I wanted to say. I hope that at least this is intuitive how these two conditions, how they enter the. Okay, so maybe one last thing. Sorry, and then I mean the big picture of this argument is the same as previously. So given SI, we construct an elementary and extension of our model with this S infinity, and then we pull it back via the resplendence argument, and this overshooting is required to express that S infinity behaves correctly on cut I and slightly above it. Okay, that's it.
Thank you, Mateusz. So let's thank our speaker. And that concludes our MOPA seminar for this semester. So please be sort of stay in touch over email. We'll announce when we will be starting again in the fall. So I'll stop the recording.